Okay, let's start uh, ideal filters. For the ideal low pass filter, transfer function with bandwidth is some frequency fu of hertz can be written as, and it can be equal to 1 or 0 uh, if frequency fall under fu, then transfer function is equal to 1, and for other frequencies it is 0 if the frequency is not falling into the fu, that is f is greater than or equal to f of u. So this one is a low pass filter, where you can see it is from minus f of u to plus f of u. We can only see in the positive side if you see. So the initial low pass means starting from 0 up to some frequency. In this case it is f of u, and it's why it is called ideal, because this cutoff frequency that you can see the fall is very that is perpendicular, basically, but in real scenario it is not perpendicular. It will take some time to drop to the that cutoff frequency that you want to filter out. So that is the difference between actual frequency that you wanted to be the cutoff frequency, and actual cutoff frequency value will be little greater than the actual cutoff frequency value. So that is in the ideal, that is not in the ideal scenario, but in practical ideal filters it will be like that. This drop will not be that sharp or perpendicular as shown in this ideal low pass filter. So that's why all these filters are called ideal, because their cutoff is same as the frequency that you want to filter. Then this is the sync function, that is the impulse response of the ideal low pass filter, very you can say the identical on the either side of t naught. uh, we can have it by doing the inverse Fourier transform of the transfer function of the ideal low pass filter, and in return you will have this equation, that is sync function, that you can see, that is t minus t naught twice of the f of u, and there is again amplitude is twice of f of u and sync function. Then we have ideal band pass filter and ideal high pass filter. So ideal high pass filter is reverse of low pass filter. In low pass filter, we want to allow frequencies only from 0 to a certain value. In the previously it was f of u, but in high pass filter we allow all frequencies except 0 to f. Like in this case, it is f of uh, l. 0 to f of l frequency will not be forwarded, other frequencies will be passed. So that's why it's called high pass filter, because we only allow high frequencies. In low pass filter we only want to allow low frequencies from 0 to a certain value, whereas in band pass filter we want to allow only a particular set of frequencies. So that is why it is called band pass filter. Then we have some realizable filters that you might have learned in the signal system and DSP subjects. The simplest example of a realizable low pass filter is an RC filter whose transfer function is given in 1.63, and it can be formed with a resistor and capacitor. That's why it's called RC filter. As you can see, now the drop from the uh, to the frequency of interest is not that sharp. You can see this is the actual frequency where we would like to drop the this cutoff, but it has been become zero, or the power becomes zero up to a point where it is like few frequencies are already added. So these are the impurities, this will cause the aliasing effect in the filter, because we allow the frequencies more than we wanted, more than we wanted to filter. So that is the clear difference between the realizable filters and ideal filters. This is the phase characteristic of the uh, RC filter. On one side it is minus pi by 2, on other side it's minus pi by 2, and it's starting from the uh, second quadrant to the third quadrant, and one side it is minus 1 over 2 pi RC, on other side it is positive 1 by 2 pi RC. Another very famous type of filter is Butterworth filter, where n is the variable. By increasing the n, you can make the drop more approaching to ideal. As you can see here, n is equal to 1 to infinity. When n is equal to infinity, the drop is like to the ideal filter, but we cannot have n is equal to infinity. But as we increase the n, the system or the design of the filter become more complex, because you will have more power here. That more power will increase this particular ratio, and it is in the square root, so the transfer function will have the lower values because it is in the denominator, and it will become smaller and smaller as we increase the n. These are the popular filters because they are the best approximation to the ideal in the sense of maximal flatness in the filter passband. So that is you can achieve by increasing the n, the maximal flatness in the filter band. Then we have the definitions of digital signal, bandwidth of digital data, uh, baseband versus bandpass. So an easy way to translate the spectrum of a low pass or baseband signal x of t to a higher frequency is to multiply or heterodyne the baseband signal with a carrier frequency wave cos 2 pi f of ct. So we do this by modulating the information signal, or that we call the baseband signal, with the high frequency signal that we call the carrier. So as you can see, that is the simplest way, x of t, and this one is your cos 2 pi f of ct. So multiplying the baseband signal with the carrier will shift the signal from baseband to bandpass, or the broadband signal. It will become, so x of ct is called a double-sided modulated signal after the multiplication, and from the frequency shifting theorem, that will be equal to, uh, if we apply the Fourier transform, it will become this 1.71, and generally the carrier frequency is much higher than the bandwidth of the baseband signal, that is f of c is greater than f of m, and therefore double side bandwidth will be equal to twice of the frequency of the modulating signal. So this is your baseband bandwidth, and this is your double sided bandwidth of the modulated signal. Now, what is the problem in calculating the bandwidth of digital signals? Theorems of communication and information theory are based on the assumption of strictly band limited channels, and the mathematical description of a real signal does not permit the signal to be strictly duration limited and strictly band limited. Like when we have uh, analog signal or any signal in the time domain, its representation in the you can see the frequency domain is like this one. The sync function is converted into the this in this frequency domain, and vice versa in the previous figure. So you can see in figure A we have strictly band limited signal in the time domain. So this one is band limited signal, and in B we have the frequency domain signal that we get from here, and then in the C we have strictly time limited signal, in the time domain, and in the D is in the frequency domain. So when we do calculate the frequency of an analog signal, uh, we always see the power spectral density of that signal where it lies. Like human voice, it's most of the power spectral, it's most of the power lies in from 300 hertz to 3400 hertz. So we calculate the free bandwidth of that, that is 3.1 kilohertz, and we approximate that to up to 4 kilohertz. Maybe in rare cases someone has sharp frequencies, so we allow some tolerance there, and we say it's a 4 kilohertz from 0 to 4 kilohertz. But when we recreate uh, a digital signal, so ideally its bandwidth will be infinite. Means to recreate a digital signal, you need an infinite bandwidth ideally, but there should be some way to limit this bandwidth and calculate the correct bandwidth where the information lies. Basically, the most of the information lies in a bandwidth that should be measured. So all bandwidth criteria have in common the attempt to specify a measure of the width W of a non-negative real-valued spectral density defined for all frequencies that should be less than infinity. The single-sided power spectral density for a single heterodyne pulse x of ct takes the analytical form. So this one is in the uh, time domain. With respect to frequency, you can see we have a frequency of interest and we have a carrier frequency. So there are different definitions or the bandwidth criteria to calculate the bandwidth of a digital signal. Differently, we have half power bandwidth, equivalent, rectangular or noise equivalent bandwidth, null to null bandwidth, fractional power, uh, containment bandwidth, bounded spectral power spectral density, and absolute bandwidth. So from the figure you can see most of the power or the information may lie in the main lobe of this signal. So the half power bandwidth will be like uh, this one, that is 3 dB drop, 0.701, 7.07. We also call this RMS value. So we only take this particular range of frequencies where most of the power lies, and a B is your equivalent rectangular noise. In that case, we almost take a first lobe frequencies into consideration, and then null to null from where it drops, and on the other side where it ends, and then we have fractional power, that is the D. We increase the side bands now. We take the first side band in that, and bounded spectral we take the second side, and in absolute bandwidth we took all the side bands into consideration. So as we go, the bandwidth will increase, but you can see the power with the frequency is decreasing. The central frequency has the most power here, but as we go from either on right or left, you can see the power with the frequency is decreasing. So we have to decide up to what point we have to take these frequencies so that information should not be lost. So the one definition is to take the half power where we might lose some information. Second definition is equivalent rectangular noise. We still uh, maybe we don't lose some information because the frequency in between the uh, null and to the equivalent noise power is very minimum power here, so maybe no information will be recovered here. And as we progress, you can include the sidebands depending on the information. But when you take the main lobe, that is sufficient for the information, uh, and no information cannot be lost using this definition, either A or B. Okay. So the bandwidth of digital signal is always a dilemma, and we have different different definitions for that, but we try to use the best option from that, like in uh, when we have this FM frequency modulation. In that we have many sidebands. So there we have many criteria to calculate the bandwidth. There are at least two different formulas to calculate the bandwidth of the FM modulated signal. Because as you see here, we have a main lobe, and this signal is not the band limited signal. Okay. In the previous slide, if you go back, see this one. This is time domain signal, and this one is in the frequency domain signal, and it is like band limited. See, so you can say the bandwidth of the signal is very much from the figure. The bandwidth from this point to this point. So that is the bandwidth of the signal. However, when we have a signal, same signal, rectangular signal in the time domain, and we convert it into the frequency domain, it becomes this signal. That is not the band limited signal. You can see it has side lobes as well. So now, how you will calculate the bandwidth of the signals? So to calculate the bandwidth of the signal was very easy from here to here. But for this signal, we have these side lobes, and they will be like up to infinite. So you take the absolute bandwidth, or from only one sideband, or from one lobe to another lobe, or the noise equivalent power bandwidth, or the half power bandwidth. So that is the question. So depending on the assumptions and calculations, we always take different definition of bandwidth for different applications. Like for real-time communication, where we don't have any uh, room to lose any information, we might go with the absolute bandwidth. But with the non-sensitive data, where we can understand what will be in between, we might go with the half power bandwidth. So that is the reason we have different definitions of bandwidth for this digital signal when it is not band limited. Okay. If you have any other questions, you can ask. Then we will move to the next lecture. So the first block diagram in this typical digital communication system is the formatting. So we will see the formatting. Uh, and other things in this lecture. So this is an example. You can see example is in ASCII alphabets, numbers and symbols are encoded using a 7-bit code. So this ASCII is used in your keyboard. If you see your keyboard, you will find alphabets and numbers, special keys, uh, alphabets from A to Z, numbers from 1 to 0, 0 to 9, and a special punctuation uh, like question mark, full stop, comma, and other signs. So all these things are represented on the back end through ASCII code. Like in this example, particularly we have typed USA from our keyboard. Any other word you can type as well. So on the when you type this one USA, the computer may not understand. So the ASCII will convert that alphabets into the ASCII 7-bit code, and that is consist on one and zeros, the binary language that computer understand. So and then that can be converted into different array digits. As you can see, that is the next step where we have converted into the hexadecimal 16 array digit, that hexadecimal symbols for the further processing. So how it is done, we have an ASCII table, you can see here. And if you see U, you will find it is here. So U is here, you can see 1010 on one side, and on other side is 101. So these are 7 bits that we take for U. Similarly for S, it is 1100 and 101, and A, uh, A is here, it is 1000 and 100. See, 1010 1010 011 and A1, all zeros, and 001. So the first 4 bits are this one. These are your first 4 bits. For U it is 1010. See, for U 1010, and the remaining 3 bits are 101. Like you can see here, 5, 6, 7, and these are your 1, 2, 3, 4, 5, 6, 7. So this is how we convert alphabets or numbers using ASCII table. So we use the ASCII table to convert this input in the alphabets into the 7-bit ASCII code. Next step is to convert this 7-bit ASCII code into 16 array digits. 16 array digits basically the hexadecimal number that is 2 power 4, where we will make the groups of 4 bits. So this is 7, 7, and 7, that is 21. Okay, so 21 divided by 4. So we can have the 5 numbers and 1 bit extra. So we can leave the first bit and we convert the rest of the bits into the 16 array digits into hexadecimal. So 0101, that you convert, that is 2 power 0, 2 power 1, and 2 power 2, and 2 power 5. So that will be at 2 power 4, 2 power 2, that is 4. We have 4 1 here, so 4 we will count 4, and 2 power 0 we have 1 here, so that will be equal to 5. Similarly, we convert waste into that. In that we have also C, that that is after, I think, 11, 11, 12. For 12 is A, 13 is B, 14 is C, 15 is D, like something like that in hexadecimal, and 0001 for 1. You can also use the 8 array digits symbols, 6-bit ASCII coding here, then 8 array waveforms will be used. This is again 6-bit and 32 array symbols, and then we have the 32 array waveforms. So that is the process. You provided your input through your keyboard in the alphabets or alphanumericals, and that will be converted into 7-bit ASCII or 6-bit ASCII, whatever the standard your laptop or computer is using. Then they will be converted into different uh, array digit symbols. Can be 8 array, can be 32, whatever the symbols we are using here, that waveforms will be generated. Same number of waveforms will be there, like 8 array, that means 2 power 3. So total 8 waveforms can be here. So we can represent 8 different data here. Similarly, here we have 32, that is 2 power 5. uh, 5 uh, 2 power 5 is 32, so 32 different waveforms can be generated for different type of data. As you can see, for 20 it is S20T. So for every uh, symbol we will have a different waveform. So this is called formatting, uh, and how we transmit the data right from here in the alphabets and into the waveform, because data on the physical line cannot be transmitted into alphabets or into the zeros and ones. It will be transmitted in terms of the voltage levels in the waveforms. So on the physical line, uh, if you are on the connected to the internet via wired or wireless, your data will be communicated through waveforms, and these waveforms are the voltage levels or the current levels that will be used to represent your data. So that is the first step that we are saying, we are calling it as the formatting. And we have used the ASCII code, 7-bit ASCII code, maybe 6-bit, depending on the machine. Then transmit and receive formatting, transition from information source to digital symbols and to the information receiver. So sync is here your receiver. So it's not the person to whom you want to fetch your data. Source, the person who is generating the data, and you can see here digital information. No need to convert. It will go to the waveform encoder where waves will be generated, or you can say that is the modulation, and goes to the transmitter channel to the receiver, waveform decoder or the demodulator, and your digital data that was transmitted is received back to here. Similarly, if you have the text information like we do here, ABC, we type from our keyboard or from our mobile, that is again in the digital form, but it need a coding, like we do use the ASCII coding here. That will be used here, and that will be again modulated or waveform encoded and then transmitted. If the information is analog, then it first need to be converted into digital, For that, we use the sampler, quantizer, and the coder. That is the last step where we will use this uh, ASCII code and 8 array or 16 array, whatever, depending on the type of waveform encoder we are using. Then it goes to transmitter, and on the other side, the same process will repeat. The digital data comes here, demodulated here, decoded, so you can convert that into textual information. If it is analog information, it will pass through low pass filter. So this low pass filter will be the same as the uh, analog information source. If the analog information source is human voice, that its frequency is up to 4 kilohertz. So low pass filter will be from 0 to 4 kilohertz. It will only allow frequencies up to 4 kilohertz, and rest of the frequencies will be blocked, will not be passed, and that is how we receive our analog information. So for different three sources, we have three different processing steps. As you can see, the best one, if we have the digital information, then no need of coding or conversion required. You just need the modulation before the transmission, and transmitter can be an antenna or can be any other device depending on the type of communication you are using, whether it is wired or wireless. If it is a wired, then this can be a transcoder. If it is wireless, this can be an antenna, and channel can be wired or wireless both. Receiver same, it can be an antenna, it can be a transducer, and it will receive data from the transmitter and will process it accordingly. Then we have character coding, that is textual information. A textual information is a sequence of alphanumeric characters that you can type from your keyboard or from the mobile. Alphanumeric and symbolic information are encoded into digital bits using one of several standard formats, example ASCII and EBCDIC. We have already seen the ASCII. ASCII has a table. Using that table, you can convert alphanumeric characters into the sequence of textual information. That textual information will be converted into the sequence of digital bits. Like here, we have textual message. Maybe I am taking your class. There may be a message encode using the ASCII. Then we have this uh, digital bits, or you can see the binary. That will be group of k bits. That is, if you want to do the AIM array, and if it is AIM array, then we have the waveform encoder. Otherwise, you can take it to the directly to the waveform encoder and you can transmit it. So these are two ways. If you use these bits directly, then it will be low and high, low voltage and high voltage. If you are using the encoder, waveform encoder, modulator, and with the AIM array, then in the symbols, group a few bits will be transmitted. Then we have this conversion for the analog signals, or the transmission of analog signals can be done through the digital communication transmitter through conversion using three steps. That is sampling, quantization, and digital modulation, and then we can transmit that signal. The first two steps are very important: sampling and quantization. Uh, that basically convert a continuous signal, that is an analog signal, into a discrete time and discrete valued signal. At the start, at the input, analog signal is continuous time, continuous valued signal. Then it is converted into uh, continuous time but discrete value signal. and then it becomes discrete time and discrete value signal after the quantization. So let's see what is sampling. So sampling is the process of converting a continuous time analog signal x of at into a discrete time signal by taking the samples at discrete time intervals, and sampling analog signals makes them discrete in time but still continuous valued. And if done properly, that is, Nyquist theorem is satisfied, sampling does not introduce distortion. The value of the function at the sampling points, that is called sampled values, and sampling interval, that is the time that separates sampling points interval between samples, T of S. If the signal is slowly varying, then fewer samples per second will be required than if the waveform is rapidly varying. So the optimum sampling rate depends on the maximum frequency component present in the signal. So again, in sampling, we need to take the frequency into consideration, because frequency that will mirror the change in the analog signal. So if I say a signal is of 2 kilohertz, that means it is being transmitted at a rate of 2000 cycles per second. So we will sample this analog signal accordingly, as the Nyquist theorem is said that the sample rate should be greater than or equal to twice of the maximum frequency. It is not equal, but it says greater than the twice of the maximum frequency. We have three types of sampling: undersampling, uh, undersampling, sampling, and oversampling. Are the sampling at the this Nyquist rate, that is the at exact value of twice of maximum frequency. One will be less than the twice of the maximum frequency, and one will be greater than the twice of the maximum frequency. That is undersampling, real sampling, or the Nyquist sampling, and the oversampling. In real-time communication, we always prefer to have oversampling, because that will not introduce any distortion in the signal. But if we go with the exact Nyquist sampling, uh, like if we have 4 kilohertz of information, then the sampling same number of samples or the will be equal to twice of the maximum frequency, that will be 8 kilohertz. That will may create some aliasing effect that we will see as we uh, progress in this lecture. But at this time, you should consider the maximum frequency component present in the signal to determine its sampling rate. So this conversion from analog to digital is a two-step process. One is sampling and one is quantization. We already define what is sampling, that convert a continuous time analog signal to discrete time continuous valued signal, and is obtained by taking the samples of analog signal at discrete time intervals, whereas quantization convert from discrete time continuous valued signal to discrete time discrete valued signal. So the sampling rate or sampling frequency, the rate at which the signal is sampled, that is expressed as the number of samples per second, reciprocal of the sampling interval. So one rate is determined from the highest frequency component of the signal, that we say f of m, that is the maximum frequency component in the signal, and another is sampling rate, that is how many samples we have per second. So Nyquist criterion say that if the sampling is performed at a proper rate, what is that proper rate? That is, if a signal is sampled at a rate at least but not exactly equal to twice the maximum frequency component of the waveform, then the waveform can be exactly reconstructed from the samples without any distortion. So it says that the frequency or the sampling rate should be greater than or equal to twice of the maximum frequency. If we done that, then the analog signal can be reconstructed from the samples without any distortion. So if we done that, if it is done at the proper rate, no information is lost about the original signal and it can be properly reconstructed later on. So this statement is, at this time it says that f of s, that is sampling interval or the sampling rate, should be greater than or equal to twice of the maximum frequency. In the coming slide we will see that this will change from this statement to sampling interval should be greater than twice of the maximum frequency. Then we have ideal sampling or impulse sampling, uh, where we have the x of s, that is the sampling uh, signal x of st is equal to x of t multiplied with the train of impulses, and then we take the Fourier transform, and in the end it will become like this. So this is your train of impulses multiplied with the analog signal, and we take its Fourier transform and we solve it, and in the end it says that is equal to 1 over t of s, that is your sampling interval or the sample rate. N is the number of impulses, that is from minus infinity to infinity, and x of f minus n over t of f. So here n is the number of samples or the impulses that we want to convert the analog signal into, and this n depend on the frequency uh, of the highest frequency component in the x of t. So if R of s, that is sampling rate, is less than twice of the bandwidth, here B represent the maximum frequency component in the analog signal. If sampling rate, if we take the samples less than at the rate of twice of the maximum frequency component, then aliasing will occur, that is the overlapping of the spectral If signal is not strictly band limited, then it must be passed through a low pass filter before sampling. Means if you have any doubt that the signal may have the information in the frequencies other than the restricted frequency, like input signal from human from its vocal cords, supposed to be from up to 4 kilohertz. But if you're not sure that it may have some components after the 4 kilohertz, maybe 4.1, 4.2, so you should use a low pass filter and limit the input source up to 4 kilohertz using the low pass filter. If you have any doubts that the signal is not strictly band limited. So fundamental rule of sampling criterion is that the value of the sampling frequency must be greater than twice the highest signal frequency of the signal. Basically, the literature writes this one as the maximum frequency, but basically this is not the maximum frequency, this is the maximum frequency component, highest frequency component available in the analog signal. So because an analog signal ranges from a low frequency to a high frequency, so in that frequency it will have a highest frequency component. In that information lies, so we will take that component, that is the highest frequency component, and mix that frequency component twice of that, and that will be equal to your Nyquist rate, or the sampling rate at which samples should be made from that analog signal. Then we have these types of sampling: ideal sampling, natural sampling, and flat top sampling. So ideal sampling is the one where we multiply the input analog signal with the impulses, and that is x of t into impulse x of t, and impulse is equal to 1 at t is equal to 0, and uh, elsewhere it is 0. So the equation will become like, after Fourier series, it will become like this one: 1 over t of s n minus infinity to infinity e j n omega t, omega naught t, and omega st, and omega st is equal to 2 pi over t of s. T of s is the sampling interval. T of s is called the Nyquist interval or the sampling interval. It is the longest time interval that can be used for sampling a band limited signal and still allow reconstruction of the signal at the receiver without distortion. So in between the two samples, the difference is called your T of s, that is the sampling interval or the Nyquist interval, and this is 0 to t of s, 2 t of s, 3 t of s, and 4 t of s. So in between we have 1 t of s. So this is your analog signal in the time domain, and in frequency domain it is represented as a band limited signal from minus f of m to f of m. This is your impulse train in the time domain. These are in your frequency domain. We multiply x of t with the impulse, the result will be like this one, and in frequency domain it will be look like this. Every different frequency we have a signal, a rectangular signal, but that's not the ideal rectangular signal. So this is what we have got after the sampling. But if we follow the Nyquist criterion, then you can recreate this signal actual analog signal from the sampled signal that is look like this one. Okay, we take a break of 10 minutes. We will continue after the break from this slide. So after the sampling, when we convert the sampled signal, that is continuous valued discrete time signal, using Fourier transform, you will be getting something like this. For every impulse, we will have a square wave signal, though it is not ideal, but it is like something like this. Now, from here, it can be a start of the aliasing. How? Let's see. This is the same figure that we have on the previous slide. So, if we use the filter, so it will, you can recover the one of these on the actual frequencies from, this is the thing that we have sampled. ये इसको हमने sample किया था. अगर आप पीछे जाएं, if you go back, see this one. This is from minus f of m to f of m. This is the Fourier transform or Fourier representation of the analog signal. So we need to recover this one. So if this signal is, you can say, the free from other signals, we can filter out this particular signal and we can convert this using inverse Fourier transform into the time domain signal representation that we have this one. But what if after the sampling, due to the rate at which we have sampled, if these different samples overlap each other, then you can see these frequencies are not separate. Like this one is independent from other frequencies. We can filter it out, but we cannot filter out this one because the frequencies are overlapping at this point and at this point and in other parts as well. So that is called aliasing effect, and it happens when we take the sample rate equal to twice of the maximum frequency or less than twice of the maximum frequency. But you will say that how? So assume that the cutoff frequency, this happened due to the filter that we use to filter out the analog signal if it is not strictly band limited. If you see the previously, it says that somewhere it says low pass filter. If a signal is not strictly band limited, then it must be passed through a low pass filter. Now this low pass filter, it's not the ideal low pass filter. That will be a real low pass filter. So it's drop from on for the cutoff frequency where you want to cut the filter out the signal, will be few hertz more than the actual frequency. Let's suppose we are trying to filter out the signal at f1 frequency. It might have the cutoff frequency equal to f1 plus 100 hertz, 200 hertz, maybe 0.5 kilohertz. So the cutoff frequency will always be greater than the frequency of interest that where we like to filter out. So it is always a good practice to take the sampling rate, sampling frequency f of s greater than the twice of the highest frequency component. If you say that the highest frequency component present in the signal is 3400 hertz, as in case of the human voice, we take the highest frequency component as the 4 kilohertz. So see, we have a margin of 600 hertz there. In case if low pass filter cutoff frequency goes beyond 3400 hertz, so it will be in between 3400 and 4 kilohertz. So actually we are taking sampling frequency greater than the twice of the highest frequency component in the analog signal. So to make ensure that when we convert the signal into digital discrete time valued signal, the signal should be properly recovered like this one or like this one. It should not be like this one where the signals are overlapping each other and creating aliasing. In that case, we cannot recover the signal without distortion. This will create some distortion when we recover the signal because two signals are overlapping here. Understood? So see, now it says as long as sampling frequency is greater than twice of the maximum frequency, no overlap of repeated replicas will occur in excess of if, and the minimum sampling criterion condition is satisfied as f of s should be greater than, not equal to, should be greater than twice of the maximum frequency component or the highest frequency component available in the analog signal. So a finite energy function x of t can be completely reconstructed from a sample value x of nt of s with provided that the sampling frequency or sampling interval should be less than or equal to 1 over twice of the maximum frequency. So that is in the terms of the uh, sampling interval. You can rearrange this equation, it will gives you the same as this one, but here we have greater than or equal to this one. But if you want to make sure that there should be no aliasing, then you should go for the sampling frequency should be greater than twice of the maximum frequency or highest frequency component. If you take the equal frequency, like in case of human voice, we know that its actual frequency is actual bandwidth is 3.1 kilohertz. Actual range is from 300 hertz to 3400 hertz. That is 3.1 kilohertz. So the sampling rate should be equal to 6.2 kilohertz. But we never take 6.2 kilohertz. We always take 8 kilohertz. That is 1.8 kilohertz extra than the actual frequency component, just to avoid repeated replicas overlapping each other, so that we can reconstruct the signal properly. Is it clear? This means the output is simply the replication of the original signal at discrete intervals, like shown in here. So every signal is separate from the other one, and you can easily filter out this particular sample and reconstruct the analog signal. In practice, we cannot perform ideal sampling because it is too difficult to create a train of impulses. Rather than that, we take a train of rectangular pulses with a narrow width tau. So that is how we can approximate a train of impulses using a train of very thin rectangular pulses, as you can see in the figure. Fourier transform of impulse train is another impulse train. Convolution with an impulse train is a shifting operation. You know that better than me from the signaling systems. So if you multiply x of t by a train of rectangular pulses, we obtain a great gated waveform that approximates the ideal sample waveform known as natural sampling or gating, as you can see in figure 2.8, and where we multiplied x of t analog signal with the rectangular pulses, and in the end we will get uh, this particular shape, because a rectangular pulse Fourier transform will be a sinc function. So that is something like a sinc function. Each pulse in x of pt has width t of s and amplitude 1 over ts. The top of each pulse follows the variation of the signal being sampled, and x of s of f is the replication of x of f periodically for every f of s hertz, and it's weighted by C of n, that is Fourier series coefficient. The problem with a natural sample waveform is that the tops of the sample pulses are not flat. It is not compatible with a digital system since the amplitude of each sample has infinite number of possible values. Another technique known as flat top sampling is used to alleviate this problem. So see here, the samples top are not flat, they are at an angle with respect to the analog signal. So these angles can be infinite, so this cannot be deemed as a practical sampling. However, we can make some changes. We make these tops as a flat and we call this flat top sampling. Then we can say that it's an uh, achievable or the practical sampling. So natural sampling and flat top sampling are the same. The difference is that here the tops of the samples are flat. Using sample and hold technique, we do the tops of the samples of the natural sampling as flat. Then it is called flat top sampling. Here the pulse is held to a constant height for the whole sample period. Flat top sampling is obtained by convolution of the signal obtained after the sampling with a unity amplitude rectangular pulse. This technique is used to realize sample and hold operation. Input signal is continuously sampled and then value is held as far as it takes for the A to D to require its value. So we stop here. We will continue from this flat top sampling in the next class. If you have any questions, you can ask.